in 3 distinct segments. Because my slides are full screen, I can't keep an eye on the chat window, so I'll rely on you, Galia or Dima, to just stop me. Otherwise, after each segment, we are going to take a quick break and see if there are any questions or comments. Okay, great. Okay, so I plan to report on ongoing work with Suresh Eswarathasan at Dalhousie University on the restriction of Laplace-Beltrami eigenfunctions to subsets of manifolds. There is a large body of work in harmonic analysis where properties of very well-behaved geometric sets are extended to a much more general setting that lacks those regular geometric structures. Our work falls in this category. Let's get started. Throughout this talk, capital M will denote a compact Riemannian manifold without boundary of dimension d. The Riemannian metric G endows M both with a topology and a canonical volume measure. The Lebesgue spaces on M, which we denote by LP of M, are defined using this natural measure. The Laplace-Beltrami operator, capital delta on M, is a second-order elliptic partial differential operator defined by the composition of two linear operators, divergence of the gradient. The spectrum of the Laplacian is a discrete sequence of non-positive numbers, which we denote by negative lambda k square. The sequence lambda k is non-negative and strictly monotone, increasing to plus infinity. E sub lambda will be our notation for the eigenspace of square integrable functions corresponding to the eigenvalue negative lambda square. It is a well-known fact that E sub lambda is always finite dimensional, and the space L2 of M admits an orthogonal decomposition in terms of these eigenspaces. Most of the results that we will discuss today hold in full generality in the context of an arbitrary compact Riemannian manifold M, but for specificity, it helps to keep a couple of examples in mind. One is the d-dimensional unit torus. Here, the Laplacian is the constant coefficient operator that we all know, and the basis of eigenfunctions is nothing other than the Fourier basis consisting of complex exponentials. Another example to keep in mind is the d-dimensional unit sphere in R d+1. Here the Laplacian is no longer constant coefficient, but still has an explicit representation in terms of the spherical coordinates. The eigenvalues grow quadratically in K, and the kth eigenspace consists precisely of the spherical harmonics of degree K. An overarching question in the field is to understand the long-term behavior of the eigenfunctions phi lambda as lambda goes to infinity. This is often referred to as high-energy asymptotics. For example, how do these eigenfunctions grow or concentrate? Where do they take large values or small values? And how large or how small can these values be? Such questions are inherently qualitative, but there is an amazing variety of quantitative formulations all trying to get at these core issues in many different ways. In the next few slides, let us look at a small sample of such questions, which will also pave the way for the problem that we are interested in. One way to study long-term behavior of eigenfunctions is through semi-classical Wigner measures. This for us will be a path not taken, so I will be very brief and rough. Suppose we have an ordered orthonormal basis for each eigenspace. Let us denote that basis elements by psi kj for the kth eigenspace E sub lambda k. Stringing these basis elements together, we arrive at an ordered, countably infinite orthonormal basis of L2 of M. Each member of the basis defines a probability measure on the manifold M, and through pseudo-differential operator theory, one can lift this to a probability measure on the cotangent bundle T star M. We have denoted this collection of probability measures by UKJ. The set of such probability measures sitting on the cotangent bundle is weak star sequentially compact, but what are the weak star limit points of these measures? How does the collection of limiting measures depend on the choice of orthonormal basis, for example? Also, is a given limiting measure easily accessible? What does one mean by the accessibility of a limiting measure anyway? Well, here is one option. One could look at a maximal subsequence of measures UKJ that converges to this limiting measure, then ask what is the density of such a subsequence relative to the entire sequence. Based on physical considerations, one expects most eigenfunctions to equidistribute. In other words, for the limiting measure to be uniform, but can there be exceptional subsequences that give rise to other measures? The slide here gives an incomplete list of some of the pioneers and major architects in this field who have utilized different assumptions on the underlying space, capital M, to deliver powerful results on the limiting measures, sometimes eliminating certain possibilities of exceptional sequences, and in some situations showing that such exceptional sequences simply do not exist. Another way of measuring growth of eigenfunctions is via Lebesgue norms. Since capital M is compact, by Holder's inequality, we know that the LP norm of any function on M has to be larger than the L2 norm if P is larger than or equal to 2. But is there a cap on the growth rate of eigenfunctions? In other words, can one find an exponent delta P such that for any eigenspace E sub lambda, the LP norm of an eigenfunction phi sub lambda in E sub lambda is no bigger than a constant multiple of lambda to the power of delta P, provided phi sub lambda is L2 normalized. I'm going to refer to a relation of this form as a linear estimate. One can then ask for finer multilinear estimates that can be obtained by investigating the interaction of eigenfunctions residing in possibly different eigenspaces. There has been a tremendous amount of research along these lines for more than 3 decades. On one hand, this sustained productivity has been fueled by advances in the theory of wave equation, nonlinear Schrödinger equation, and Fourier integral operators in Euclidean spaces. On the other hand, this study has contributed significantly to our understanding of these same equations on manifolds. Here is a fundamental result due to Chris Sogg on the growth of Lebesgue norms in the linear estimate paradigm. Sogg's result was for a general Riemannian manifold of arbitrary dimension d. I have quoted it here in dimension 2 so that we have some concrete numbers to refer back to later on. The result says that the LP norm on capital M of an L2 normalized eigenfunction phi lambda grows like lambda to the power of delta p, where the exponent delta p is half minus 2 over p for p larger than or equal to 6, and a quarter minus 1 over 2p for p between 2 and 6. The estimates are sharp for the two-sphere, and indeed, the Stein-Thomas restriction theorem on the sphere was an inspiration for an initial version of this result on this very special manifold. The growth of Lebesgue norms prompts one to ask a more refined question. What about restricted Lebesgue norms? What do I mean by that? Suppose that sigma is a smooth embedded submanifold of dimension n sitting inside capital M. How well behaved is an eigenfunction restricted to sigma? More precisely, given an exponent p, what is the optimal growth rate alpha p such that the LP norm of phi lambda restricted to sigma grows like lambda to the power of alpha p, where phi lambda is an eigenfunction that is L2 normalized on the entire space M. The first work in this direction is by Reznikov, and a representative result that is of immediate interest to us is due to Burq, Gerard, Szvetkov, and independently by Hu. So the next slide talks about that result. So again, the result of Burq, Gerard, Szvetkov, and Hu, they pertain to all manifolds capital M and all submanifolds thereof. To keep things simple, I have stated it here where the ambient dimension is 2 and one restricts to a curve. So n, the dimension of the submanifold sigma, is 1. Here, the growth exponent alpha p splits into two parts, staying at a quarter for p between 2 and 4, and increasing linearly in 1 over p for p between 4 and infinity, hitting half at p equal to infinity. Once again, this result is sharp on the two-sphere. For large p, any curve gamma on the two-sphere suffices to provide sharpness. For in the low p regime, one needs to look at a geodesic curve on the sphere. So maybe here's a picture just to plot, show you the plot of alpha p versus 1 over p. We'll come back to this picture again later in the talk. How should one interpret the result of Burq, Gerard, Szvetkov, and Hu? One way to view it is as an improvement over the Sobolev trace theorem, which gives bounds for general Sobolev functions when restricted to the boundary on a manifold. Such a bound for p equal to 2 would yield lambda to the 1/2, whereas the Burq-Gerard-Szvetkov Hu bound gives lambda to the power of 1/4. This gain is due to the fact that the trace is taken from a smaller, more specialized class of Laplace-Beltrami eigenfunctions. Another way to think of the BGTH bound is as a partial averaging effect. The while law, itself a major topic of research, states that the pointwise each L2 normalized eigenfunction is no larger than lambda to the power of 1/2. This exponent is in fact sharp, as one can see from the context of the sphere. Sog's bound, however, so this is a sup norm bound, so it talks about the largest possible value that phi lambda can take. However, these large values are presumably concentrated in small places. So, if you average the eigenfunctions in the LP sense for a finite p on a larger set, common sense dictates that this bound should improve. Sog's bound indicates the improvement, namely lambda to the power of 1/8 when averaged in L4 over the entire manifold. The BGTH bound falls somewhere in between. It averages over a smaller set, namely a curve, and there it indicates a gain of lambda to the power of 1/4 if averaged in L4. What do we know about the sharpness of the Burq, Gerard, Szvetkov, and Hu bound? So this is a bit of a good news, bad news story. The good news is that when viewed across the range of all two-dimensional manifolds M and all curves gamma therein, the estimate cannot be improved, as I mentioned earlier. In particular, the two-sphere is an example where the estimate is sharp. On the other hand, the estimate can be improved significantly in many instances. For example, on any manifold, if one chooses a curve of non-vanishing geodesic curvature, the exponent 1/4 at p equal to 2 improves to 1/6. On manifolds where there is a pointwise wild bound, for example, the D torus, the bound improves again, this time for all curves. So, finally, that brings me to the question that Suresh and I asked. Suppose that capital E is an arbitrary Borel subset of the manifold M. Not necessarily a submanifold, maybe not even contained in one. It is sparse in the sense that E is always Lebesgue null. It has a prescribed Hausdorff dimension and is equipped with some structure that needs to be specified and supports a probability measure mu. What can one say about the Lebesgue norm estimates of the Laplace-Beltrami eigenfunctions with respect to mu? In particular, we are looking for estimates of the form here in pink, of course with an eye to obtaining the optimal exponent alpha p that comes in the power of lambda. Among other things, we would like to find an exponent that helps us that is consistent with the earlier work of Sog and Burq, Gerard, Szvetkov, and Hu. Formulation of the problem concludes the first segment of my talk. Let's take a quick break for questions and comments before moving on to the next segment.
Lebesgue,
yeah.
Can I ask a silly question? So there is an old result, of Steve Zeldich and myself that if you have any, let's say, set on the two-sphere, which is invariant under taking the diametrically opposite point, then there is a sequence of spherical harmonics whose squares concentrate on that set. I suspect you can make the set fractal as well.
Okay.
So it's kind of just a weird thing. I mean, if you lift basically any set which is invariant under the flow, you can have a sequence of harmonics whose Wigner measures concentrate on that set. Now, it seems that if you have your favorite set, which is, let's say, invariant under reflection, and you would like eigenfunctions to concentrate in some sense on that set, then a sequence of harmonics whose limiting measure concentrates there would be a good candidate.
Yes.
So it could be interesting to see what these sequences which concentrate there, what kind of LP norms they have and things like this.
I do agree. So you see, what you described was more a question for the Wigner measure part, right?
Yes, yes.
Yes, but okay, let's see now.
But it's just a remark that
Yes.
if the square tends to concentrate on some set weakly, then you can you can have 2 points, or you can have any collection of any invariant collection. So
Yes.
but so this is just existence. We have never looked at the rate of convergence or anything. But I think it could be an interesting place to an interesting special case of to look
Yes.
an interesting set of examples for your kind of results.
I think so. So especially if the set that you describe is fractal, one natural question to ask would be that the natural fractal measure that this set supports, does it realize the best possible alpha p?
Yeah. So
Right.
that could be interesting to look at. Yes.
Yes. Okay. Any other questions, or shall we move on? Okay. All right. So before we state our main results, let's quickly refresh our memory regarding the notation. Capital M is a compact Riemannian manifold of dimension d. Sigma is a submanifold of M of dimension n. Sigma could be M itself, so n could be equal to d. Capital E is an arbitrary Borel subset of sigma, whose Hausdorff dimension is n times 1 minus epsilon. Epsilon is a small constant between 0 and 1. Epsilon could be 0. In other words, E could have full dimension, but we always require it to be Lebesgue null. We are going to define a critical exponent P naught, which is given by 4n times 1 minus epsilon, so 4 times the dimension of E, divided by d minus 1. And this is going to play a role in the statements of our main theorems. Our first main result says that any arbitrary Borel set, capital E, in a manifold will yield a family of eigenfunction restriction estimates that is almost optimal relative to its dimension. More precisely, for every kappa positive, we can find a probability measure, nu super kappa, supported on E, such that for every Laplace-Beltrami eigenfunction phi sub lambda that is L2 normalized on M, the LP norm of phi sub lambda with respect to nu grows at most like lambda to the power of alpha p. What is alpha p? Like the earlier results of Sog and Burq, Gerard, Szvetkov, and Hu, the alpha p admits a multi-part description. For large p and for integer dimensions, this matches exactly the description of the previous work. I'll come back to this point again momentarily. The threshold exponent where this transition occurs is P naught, or almost P naught, up to a multiple of the infinitesimally small kappa. Similarly, there is a fudge factor in the power of lambda as well, which has been captured in this function phi sub p lambda. What is phi sub p lambda? It's a function that grows at most like a small power, lambda to the power of kappa over p. If kappa was 0, then we would recover exactly Sogg's and Burq, Gerard, Szvetkov, and Who's bound on submanifolds. In general, though, we cannot take kappa to be equal to 0, only arbitrarily small. Of course, if p is small, then phi sub p is just a constant. Inspired by this result and for future reference, we are going to define a certain class of functions. Let psi be a function defined on the interval 1 to infinity on the positive real line. We are going to call psi a function of slow growth if at infinity it grows slower than any positive power of t. The measure theoretic basis of our results is a very simple one. Let's take a little time to review the relevant facts. Suppose that nu is a probability measure supported on a Borel set, capital E. We say that E obeys a Borel condition of order alpha if the mass that nu assigns to any ball grows in a controlled way depending on alpha. More precisely, we require that the new measure of any ball has to be at most a constant multiple of its radius raised to the power of alpha. What is this condition really trying to capture? A little bit of thought shows that the concept underpinning this definition is really the spread of the support of the measure. For example, if nu is a Dirac delta function, then the only possible value of alpha is 0. On the other hand, if nu is the Lebesgue measure on the unit square in Rd, say, then alpha is equal to d. It is therefore not a surprise that the Borel condition is intimately related to the Hausdorff dimension of a set. This connection is made precise in a classical result in geometric measure theory called Frostman's lemma. The lemma states that the Hausdorff dimension of any Borel set E is the supremum over all numbers alpha such that E supports a probability measure nu which obeys a Borel condition of order alpha. The first result that I stated, the one about eigenfunction restriction to an arbitrary set E, is in fact a consequence of a much more general phenomenon whereby any Borel condition on a measure ensures eigenfunction estimates restricted to the support of the measure. In fact, this is really our main result. Superficially, the result looks very similar to the earlier one, except that this time, instead of an arbitrary E, we assume that E supports some probability measure nu that satisfies a Borel condition of order alpha, possibly allowing for a function of slow growth. Then we show that the displayed restricted eigenfunction estimates hold. It is important to note that this result easily implies the earlier one via Frostman's lemma, the family of measures nu super kappa are precisely the ones that are needed to attain the supremum in the relation involving the Hausdorff dimension. Are these results sharp? It turns out that for large P, they are. Specifically, if the underlying manifold is the n-sphere and the measure nu obeys a ball condition for a family of balls shrinking to a point on its support, then we are able to establish a lower bound on the LP norms of the normalized spherical harmonics restricted to E. And we show that the exponent theta p in the lower bound matches the one from our upper bound for large P. So here's our old picture again with an overlay. So the blue line indicates the Burq, Gerard, Szvetkov, and Hu bound when epsilon is equal to 0. Remember, the transition there happened at p equal to 4. Now we are working in the fractal setting where the dimension is n times 1 minus n is 1. So the dimension is 1 minus epsilon for some small positive epsilon. The line now lifts off a little bit, the one in pink, and the transition happens at 1/4 times 1 over 1 minus epsilon. Okay, let's summarize where we are at. Given an arbitrary Borel set E, we are able to find a family of measures, nu kappa, supported on E, that generate near optimal eigenfunction estimates up to power loss in kappa. A natural question is, suppose we do not want to deal with an infinite family of measures. Can one find a single measure on the set E for which optimal eigenfunction restriction estimates can be attained, possibly allowing for a function of slow growth? This slide provides an affirmative answer to that question, but not for all sets E, only for generic sets E. Once again, start with a small epsilon. Sigma is a submanifold of M as before. We are able to find a measure space capital omega equipped with a probability measure P star such that almost surely, P star almost surely, every element little omega in capital omega generates a Cantor-like subset E sub omega of Hausdorff dimension n times 1 minus epsilon, which obeys an eigenfunction restriction estimate with exponent alpha p, modulo a function of slow growth. Alpha p has a two-part description that is completely aligned with the earlier work of Zog and Burq, Gerard, Szvetkov, and Hu. Namely, alpha p is the constant d minus 1 over 4 in the range of p between 2 through p naught. If p naught, provided p naught is larger than 2, and it varies linearly in 1 over p beyond p naught, reaching d minus 1 over 2 at p equals infinity. So let's briefly discuss what these growth rates mean. Our exponent, as I mentioned, is consistent with earlier work. What do I mean by consistent? It means that for large P, they have a similar formula. What's this formula? They are all half of the ambient dimension minus 1 over 2 minus 1 over p times the dimension of the set where you are taking the LP average. SOG took the average over the entire manifold capital M, so this was the dimension D. Burq, Gerard, Szvetkov, and Hu took it over the submanifold sigma of dimension n. This was n, and we did it over a set of dimension n times 1 minus epsilon, and this is exactly analogous to that formulation. In addition to obtaining new restriction estimates for sets of fractional dimension, our method gives an abundance of new sets of integer dimension that obey the Burq, Gerard, Szvetkov, and Hu estimates. For example, there are many Cantor-like sets of Hausdorff dimension 1, which are not necessarily the subset of a curve that obeys these bounds. Similarly, there are full dimensional but Lebesgue null subsets of a curve that obey such bounds as well. On a similar note, we are able to find a full dimensional but Lebesgue null subset E of capital M itself equipped with a singular measure which obeys the same linear estimates with respect to the Lebesgue norm growth as SOG's LP estimate over the entire manifold. So in a sense, what this shows is that even though submanifolds enjoy a lot of rich properties associated to the differential geometric structure, as far as eigenfunction restriction estimates go, there are many other sets of same dimension lacking those geometric structures that obey the same estimates. The exponent alpha p of lambda that we get is sharp for large p. At the moment, we are able to ensure, well, for a small p, and in this, where is this? For small p, so if p is less than p naught, our exponent is not sharp. And the cause of this non-optimality is the Lebesgue exponent p naught that we get. This is an artifact of our proof. The good news is that our analysis fails for identifiable reasons, allowing us a way forward in terms of improvement. I will return to this point at the end of my talk. I showed you this function phi p bar lambda, a function of slow growth in our genericity of optimal sets and measures. This function of slow growth, it's actually explicitly computable. Okay, so this completes the discussion of our main results. My goal next is to head out to the proof techniques. Let's stop for a moment to see if the audience has any comments.
Hi. Yeah, I forgot what P naught was. So on slide 26, could you?
Yeah, absolutely. Hang on, let me try to get back to P naught. So P naught was a threshold exponent right here. It's a 4n times 1 minus epsilon divided by d minus 1. And this is the critical threshold for us, but it's not the best possible. We think we know that this can be made better.
Okay, great. And sometimes the n times 1 minus epsilon is alpha, right?
Yes, indeed. So, okay, hang on. Whoops. I don't know why this keeps like moving up and down. Sorry. Okay. So this n times 1 minus epsilon, this is the dimension of the set E right now. But if we sort of move away from the set E and we just focus on some measure, then the alpha is the exponent that is associated with the Ball condition. if nu is the right measure for E, and what is right, meaning it's right in the sense that it realizes Frostman's lemma, then that alpha becomes n times 1 minus epsilon.
Perfect.
But
Yeah.
of course, the set E can support a whole zoo of measures, and each one of them may have a different alpha associated with it. So every such measure will give us an eigenfunction restriction estimate with that alpha, the best one, of course, being the one where alpha is equal to n times 1 minus epsilon.
Right. Perfect. Yeah.
Okay.
Thanks. That helps.
Okay. Okay, I cannot see all of you, but should I keep going?
Yes, please.
Okay, all right. So, so in terms of the proof overview, what are we going to, okay, so the last thing we talked about was this family of random Cantor sets. So what are random Cantor sets? What do they look like? So here's a picture. In our setting, we, again, I'm going to only stick to the situation where n equals 1. You start with a unit interval 0 to 1. You decompose this interval into capital N1 equal pieces. For each resulting subinterval, you flip a coin with a certain success probability P1 of landing heads. If the coin falls head, we keep that subinterval, otherwise we discard it. So in step 1, these intervals in blue are the ones for which my coin landed heads. Once the first step is concluded, and by the way, maybe I mentioned it already, we do the flipping independently for each subinterval. And once the first step is concluded, we decompose each selected interval from level 1. So we had 2 selected intervals at level 1. We decompose each one of them. So this one I have zoomed out, so that's that. And this one I have zoomed out. And we decompose each one of them into n2 equal pieces. So each interval is now of length 1 over n1, n2. And we flip another coin with a different success probability independently for each one of these finer intervals. And we keep those subintervals whenever the coin lands heads. It's important to note that because of these random flips, the iterative pattern is definitely not self-similar. Different level 1 parents will, in general, give rise to different sequences of children and even different number of children, as you can see in this picture.
Milabika, can I ask you something?
Yes.
So in level 2, the probability that you use in each of the selected ones in level 1 is different, possibly, or is the same?
It's possibly different.
Okay.
Yes, and in fact, I'm going to say a bit more on that in the very next slide. Thanks. Was that you, Christina?
That was me, yes.
I thought I recognized your voice. Okay. All right, here we go. So let's formalize this a bit more. So in order to set up a collection of random sets, we are going to need a sequence of large constants, capital N sub k, and we are going to also need a sequence of small constants, epsilon k. The constant n sub k specifies the number of subintervals that a k minus 1th level basic interval splits into. Epsilon k is related to the probability of selection, and at the kth stage, and ultimately this epsilon k is ultimately related to the Hausdorff dimension of the set. So to answer Christina's question, at the kth level, we choose a success probability p sub k, where p sub k is n to the power of n k to the power of minus epsilon k. So here is how, so by the way, this we also have this random binary sequence. This is really to keep track of which subintervals at the kth stage are chosen, or and if it's 1, then that indicates choice, and if it's 0, then that means we discard it. Okay. So here is how we represent these random Cantor sets. For every integer k, we have a multi-index boldface ik, which is of length k. Each multi-index marks a subinterval of length 1 over n1, n2, and k, and tells you how you can reach it. The first entry, little I1, signifies which of the n1 first level intervals you are in. Once I1 is fixed, I2 tells you which one of its n2 children is being considered, and so on. For each multi-index ik, there is a binary random variable xk of ik, which if 1 signifies that this interval has been selected, and 0 if it is not. Once a random variable x sub k minus 1 is 1, all its immediate successors are 0 or 1 independent. Well, if this is 0, all its children are automatically 0 because of its formula. But once you fix it, these yks are independent of xk minus 1. So the kth iterate of the Cantor construction on 0, 1 yields a set Fk, which is essentially the disjoint union of all the selected intervals at that level. The final Cantor set is the nested intersection of the iterates Fk. Capital F is a Cantor set on 0 to 1, and we can then lift it to a submanifold sigma via a coordinate chart. What are all the measures that we need to work with? One is the measure space of Cantor sets, and the other one is the measure that the Cantor set supports, which is the basis of the restriction estimates. So first of all, in order to place a measure on the Cantor family, we better make sure that the process results in a non-trivial set at the end. In other words, that the intersection is not empty. If boldface P denotes the product probability measure of the IID Bernoullis occurring at every step, then one has to check that the event of having a non-trivial limiting set is positive. The measure P star that shows up in our theorem is the measure P conditional on the event that F is non-empty. What is the measure mu on E based on which we will compute all our restricted LP norms? If mu k denotes the normalized Lebesgue measure on each fk, then mu is the weak star limit of the mu k's after being pushed forward to the manifold via the usual coordinate charts. Of course, one has to verify that such limiting measures exist. Okay, so in the little bit of time that I have left, what I'm going to do, I'll try to give a brief sketch of the proof of our main result, namely the Borel condition on measure implies eigenfunction restriction for the support of the measure. And as a warm-up, it is really instructive to revisit the highlights of the Burq, Gerard, Szvetkov, and Hu proof and assess which components of their proof go through in our context. So the Burq, Gerard, Szvetkov, and Hu proof relies on 4 important steps. The first is the preparation of the smooth spectral projector, the operator that we will eventually restrict to a curve. The second is the method of TT star, which brings 2 technical advantages. One is that it allows us to reduce the eigenfunction restriction estimate to an LP-LQ bound on the same measure space, namely the Lebesgue spaces on the curve. The other advantage is that the TT star is an operator whose integration kernel is an oscillatory integral with a non-degenerate phase function. And this suggests invoking the method of stationary phase, which is the key third step. The outcome of stationary phase is then handled by Young's convolution inequality. So let's go a tiny bit more detail for each step. The first step involves understanding the smooth spectral projector as an operator. Using results that are by now classical, this spectral projector admits a local asymptotic expansion in lambda. And the expression that I have written down here is modulo a power of lambda, the leading term in that asymptotic expansion. It is this oscillatory integral operator with the phase function given by the geodesic distance, whose restriction properties we will eventually have to decipher, but we massage it a bit more prior to that. By a polar change of coordinates, we write the operator as an integral over fibers, with the operator in each fiber acting on a function of the angular variable. If we knew that these fiber integral operators were bounded from L2 of the circle to LP of the curve, then by Minkowski's inequality, I could transfer the LP norm inside the integral and obtain an operator norm of T lambda by integrating the operator norm of the fibers. Thus, the goal is to show that such an L2-LP operator norm satisfies the claimed bound. By the method of TT star, this is equivalent to showing that TT star is bounded from LP prime of the curve to LP of the curve, with the right growth, of course. The third step takes a closer look at the operator TT star by writing down its integration kernel. This kernel is an oscillatory integral with a non-degenerate phase function. So by the method of stationary phase, we arrive at a decay rate for it in terms of lambda times t minus s. The bottom line is that because of this upper bound obtained in the method of stationary phase, TT star is actually bounded by a convolution operator because of the dependence, because S and T are related by the expression T minus S. Now, standard results kick in. Young's convolution inequality tells you which triples of exponents give rise to convolution operators being bounded on LP spaces, and plugging in the values of P0, Q0, and R0, we are able to say that the operator of interest is bounded above by a certain norm of the convolution kernel. But the convolution kernel, remember, was completely explicit, so it's easy to determine the exponents for which it is integrable. So that was Burq, Gerard, Szvetkov's proof, an overview of it. How much of it lifts to our context? It turns out that there is a robust framework for us to draw on. The first three steps that I outlined go through essentially verbatim. It fails at the last step, since Young's inequality is tied to convolutions, which in turn is connected to the translation invariance of the Lebesgue measure. There is no analog of it for general measures. However, we do have a working substitute. Suppose that capital T is an integral operator with a non-translation invariant kernel K, and adapting ideas from Schur's lemma, we show that T maps LQ to LR with an operator norm that is given by the geometric mean of two quantities A sub s and B sub s. What are they? These are the supremum of the integral k of this integration kernel k raised to the power of s in one of the variables. The exponents q, r, and s, you will notice, obey the exact same relation as Young's convolution inequality. So it then remains to estimate these objects a sub s and b sub s. We do this, so I'm reminding you what a sub s and b sub s are. In our context, we do this by decomposing the integral into dyadic pieces depending on the size of the integrand. And now you see why this brings in the ball condition in a very natural way, since the integral is really an interplay of two components, the size of the ball and the size of the integrand on the ball. The last but not the least step, so this is exactly how you see that this integral is really of the same size as this expression, which brings in the mu measure of a ball. Last but not the least step is the verification of the ball condition for the random Cantor sets, but I'm not going to talk about that right now. So let me leave you with a few open questions. We are working on obtaining optimal estimates for low p, in other words, improving the value of p naught. And this requires harnessing the oscillation inherent in the kernel, something that we have completely ignored in the current analysis. Improvements of alpha p are possible for random Cantor sets of certain curves, say the ones which have non-vanishing geodesic curvature. We are looking into that as well. Finally, if one steps away from the random framework, would it be possible to obtain good bounds for deterministic Cantor sets? For example, the standard Cantor middle third set. Right now, there seems to not even be a partial answer in this direction. I think that's all I had to say. Thank you very much.
So thank you, Milabika. Thank you very much for a great talk. Are there any questions?
Can Milabika, what you said at the very end, so what can you explain why the random Cantor sets are, you can handle them, but the deterministic, what's the obstacle with the?
Yeah.
Mm-hmm.
So I think the obstacle is the self-similarity or for deterministic Cantor sets. You see, the random Cantor sets are, we have the flexibility to make them very similar in principle to a Lebesgue measure. They are not, but it is on an average, they are, whatever that means. So we always try to cash in on the randomness, even though they are Lebesgue null sets, there are still, because of these large deviation inequalities that we can use, they are very close to their expected value in some way, and the expected value is the Lebesgue measure. Once we move away from that framework, we do not really have a good way to handle the operator anymore. The main analytical tool disappears. So we have to maybe find a combinatorial way to verify, say, the ball condition, or find or compute TT star and its integration kernel. So the short answer is our main analytical machinery disappears if randomness is taken away.
Thank you.
I have sort of a slightly different, strange question. So when this is about, also maybe about spherical harmonics, just to make things, to keep things simple. We know that random spherical harmonics have fairly small LP norm, right? On the other hand, like logarithmic or something. On the other hand, we know that there exist spherical harmonics with very, very large LP norm.
Yes.
So somehow things, so suppose you look at spherical harmonics whose LP norm grows like a certain power of lambda,
Yes.
then maybe you can somehow cover, in the space of all spherical harmonics, you can cover the set of very large ones
Yes.
by few balls in the space of all spherical harmonics. And then if you let the degree go to infinity, then you could maybe define somehow the the dimension of the set of all harmonics whose LP norm grows at a certain rate, non-typical rate, like lambda to a certain power. So I don't know, maybe I suppose this may even make sense, like on the torus with some multiplicity, arithmetic torus. But maybe some things like this were done, but so somehow the quantify how small is the set of functions whose LP norm grows too fast.
Right. So let me make sure. So I'm just trying to get back to, let's say, it seems like you are talking about a result like this. But if I understood you correctly, you want to find out the extremal phi lambda, which realizes this sharp bound. And you're saying, if I understood, it seems like a question of an
extremal
extremizer.
or faster than a random one.
Faster than a random one. Okay. Okay. Yes.
So like for Lebesgue almost all, right, things will grow very slowly, slower than any power of lambda or something like that.
Yes.
So anything that grows polynomially somehow is exceptional.
Yes.
And so you fix the power of lambda at which you would like things to grow, and then you try to see how big that set is.
Has it been done? I actually do. That sounds really interesting. Has somebody looked into the?
I'm not 100% sure. I mean,
I
think for random.
In fact, I'm sorry to interrupt you, Dima, but actually I think that at least in terms of the L infinity case, I think John and Steve had done some work in terms of classifying certain geometries where you can get eigenfunctions with maximal LP norms, meaning that they have some kind of lower bounds. So I think that at least, I mean, I think that the sphere has these kinds of things. There's some particular geometric.
Yeah. But of course, like the harmonics that are big at north and south, they are extremal for points. So a sphere is definitely one geometry where you can have exceptional things, and then I suppose just by somehow intermediate value theorem, you can have any kind of polynomial growth between the maximal possible and the logarithmic. So there will be examples. The question is, how big is the set of these examples? That's what I'm asking.
Big, okay, well.
Yeah, but I'm not sure if anyone has this. So I think this could be maybe a reasonable.
I mean, there is a really, a vibrant research community which deals with specifically this type of questions to look at functional inequalities and study how large is the set of extremizers, or as you move away from the set of extremizers, what kind of gain or improvement in the estimate is possible. I'm afraid I have never looked at this myself, and I'm not sure, as of now, right now, I can't think of any work which addresses this issue for the spherical harmonics, but I try to see if I can find anything on it.
Oh, thank you very much. Are there some other questions?
Yeah, so thank you for the amazing talk. It was so clear, and the results are really incredible. I had two questions. One is a micro question and one's a macro question.
Okay.
So the micro question is, so if you go to the end of your slides where you have fractal Young.
Yes. Yes.
That was that's a very interesting slide for me. And I was just wondering, trying to connect that slide with what you ended your talk with. You said even for the middle third Cantor set, right?
Yes, yes.
That you don't know how to do this. So is there a conjecture to be made here about the middle third Cantor set?
So, you know, that's this trying to find out what is the best growth rate. I mean, I should say it's a problem very close to my heart. I mean, I would say the conjecture, of course, is the one that I would take the natural Cantor measure, and I would say that I'm aiming for an estimate like, let's show you our main result. Here. So let's say, forget this line, okay? So this, let's take our natural Cantor measure nu. What is the best alpha p that we can get for that measure? For all p? That would be the question, right?
Yes.
And on one hand, we do have some things. For example, for the natural Cantor measure, we can say that such a relation holds if alpha is log 2 over log 3.
Right.
Because that's the Hausdorff dimension of the standard Cantor set. However, we also noted that this P star, which later in this context of V, we called P naught, is not optimal. So we don't really know how to go beyond this at this point. But this, I think, for large P regime remains optimal. It's really for smaller P's that we don't really know how to get a handle on the Cantor middle third set. Part of the reason is the following. In the proof, I was showing you this integration kernel S. Where do we go? Here. I was showing you this integration kernel which appears as an oscillatory integral. In the case of the Cantor middle third set, we are integrating this non-degenerate phase function against the natural measure on the Cantor middle third set. How does one estimate such an integral? That, I think, is, at least for me, the main sticking point.
Wow.
In the case of random Cantor measures, we are able to say that whatever one expects from the method of stationary phase can be lifted. And I simply don't know how to bypass that issue for a deterministic self-similar measure as of now.
Yeah, my only reaction is wow. It's a really amazing question.
Yeah.
So thank you. That was my micro question. Now my macro question is very naive, and I'm sure the experts in the audience, including yourself, will laugh at this, but I still want to ask it because it's just was bugging me at the beginning of the talk. So at the beginning.
Hello?
Oh, sorry. So can you hear me?
Are you still there? I think I lost the audio.
We can hear you.
Sorry.
We can hear you.
Okay, I think I lost the macro question.
Yeah. So the macro. Can you hear me now?
Yes, I can hear you now.
Sorry. Yeah. So the macro question is very naive. So in the first part of your talk, where you were surveying results, your examples were always taken from SD or TD. So the sphere and the torus. And sometimes you said that, such and such result was sharp, and then you mentioned the sphere.
Yes.
So my question is, like, even in D equals 2, what is known for, like, say, negative curvature? So say you have compact Riemann surfaces of genus greater than or equal to 2.
Yes.
Then what happens to that, this is a vague question and it's naive, but if you could say something about why you avoided talking about negative curvature.
That's a good question. So you see, I think we came at it from the point of view of making no assumptions on the manifold at all. We first wanted to obtain estimates that hold in complete generality, and that was the results that we stated. But having obtained those results that hold for all m, then our next level question was to ask, are these estimates realized for some m? And that's how we gravitated towards the D sphere.
I see.
But as I was saying in that last slide, are a number of refined questions out that for special m's, can one improve these exponents that one gets? In particular, I think this ties to your question. If one looks at manifolds of negative curvature, what is the right alpha p for those? So this is actually something that we are very much interested in. I don't have a good answer to your question now. My hope would be that for manifolds of negative curvature, this alpha p that we get would be different, or maybe in certain cases much better than what we showed in the general case. But as of now, I don't know if this question has been addressed for spaces of negative curvature for this problem. I mean, manifolds of negative curvature has been widely studied in many contexts, but I don't know if, especially for eigenfunction restriction estimates in terms of Lebesgue norms. But maybe Suresh would know.
Yes, it's very likely the results improve in negative curvature. I mean, there have been a swath of previous results improving the SOG bound, and actually, I think some students of Chris, and I think some students of Chris have worked a lot on improving the restriction bounds in negative curvature. Chris being Chris SOG, excuse me.
Yeah.
But I think if you don't make an assumption that the manifold is arithmetic or anything, then improvements are probably would be logarithmic, right? I mean, maybe some power of logarithm. So if just you assume negative curvature, nothing else, then it's not, we do not know if there is a polynomial improvement. There are conjectures that L infinity norm should grow slower than any power of an eigenvalue, but that conjecture seems very, very difficult. And in some cases, on some like arithmetic free manifolds, there are counterexamples at certain points, at Wigner points.
I think that, in fact, the results of Simon Marshall and other people in kind of the Sarnak school, where they have looked at particular arithmetic cases, and they have had polynomial improvements.
No. In arithmetic cases, you can, yes. But if you just assume negative curvature, well, okay, I may be wrong.
I think that's very hard to do, right? I mean, it hasn't been done in the last 30 years.
Yeah. So, but I'm not sure if like restriction estimates, if the logarithmic improvement. I know that, for example, Reznikov, I think he started by looking at geodesic circles in negative curvature.
I see.
In fact, I think his result is actually weaker than Burq, Gerard, Szvetkov's, which is more general. So it's one of those few cases where he used arithmetic structure, but somehow it didn't give. I didn't give a result that was better than using a general method. It was just.
I think he just used constant negative curvature. He didn't use arithmetic, but maybe I'm wrong.
No, he was using arithmetic structure.
He was using, okay.